Okay, group. In this section here, I want to pull back a little bit from gases and recall stoichiometry. Let's consider a reaction here that we've looked at before, which is the production of hydrochloric acid or aqueous hydrogen chloride if it's bubbled into water. In this particular reaction, it's a 1-to-1 molar ratio. However, when we're working with gases, quite often we're not going to be massing the gases on a balance the way we would with solids. So a more convenient measure or more appropriate measure for the reactant amounts would be a volume. And this is what scientists were interested in, was this idea of how do gases combine. Now we looked at Charles' law and Gay-Lussac's law and Boyle's law in the earlier sections on gas laws. And here, another law that Gay-Lussac looked at, Joseph Gay-Lussac, this is in the early 1800s, working with gas phase reactions. He looked at this reaction and he found that approximately 1 liter of hydrogen gas combined with 1 liter of chlorine gas to produce exactly double the volume, 2 liters of hydrogen chloride. So his discovery led to this statement, which was a law. And a law is just something that is observed repeatedly to the point where it can be formally stated as a law. For a particular chemical reaction involving gases that are at the same pressure and temperature, the volumes of reactant and product gases are always in fixed whole number ratios. Emphasis there on the volumes, also on fixed whole number ratios. So that's really convenient because we're used to working with whole number ratios for chemical reactions. We would use mole ratios. Now we can use volume ratios. Now the explanation for this is something that came a little bit afterwards, but let's have a look at practically what that might look like. Here's another chemical reaction, a volume ratio of hydrogen and nitrogen to form the molecular compound ammonia. In this case, the balanced chemical reaction requires 1 to 3 parts by moles, and it turns out that this ratio would also be observed by volume, meaning that 1 part, whether it be a liter of nitrogen gas, would require 3 parts of hydrogen gas, and as a result, the mole ratio for the product is also observed in the amount of gas produced as a volume. Now, when we look at these ratios, we might be tempted to think that that means that 1 liter is the equivalent of 1 mole, or 3 liters equivalent to 3 moles. That's not what we're saying here. What we are saying is that the amounts that the reactants combine are in specific ratios, either by volume or by moles. Now, the reason for this has to be based on the number of particles, because we know that chemical reactions like the one here definitely observe a mole ratio. And this is, of course, what Avogadro came up with. Spelling mistake on Avogadro there, but Avogadro we've seen before as the Avogadro's constant for the molar amount for particles, and the hypothesis preceded the empirical, but a theory was proposed, Avogadro's theory of gases, that these volumes of gases that are under the same pressure and temperature must contain the same number of molecules if we're talking about equal volumes. So that would allow for 2 liters of gas to have twice as many particles as 1 liter, which would be consistent with the mole ratio. And in the case of the hydrogen plus chlorine to hydrogen chloride, in that case the mole ratio is 1 to 1. So we would need a mole of each, or equal numbers of moles of each, and in that case we would need equal volumes of each at the same pressure and temperature, because Avogadro hypothesized that those equal volumes would contain the same number of molecules. Now, this is really a result of the structure of gases at a molecular level. We would have individual particles, And if the pressures of the gases are the same and the volumes are the same, then it must be because we have the same number of particles striking the container walls. That would produce the same pressure. All right, so this Avogadro's theory of gases works well with the law of combining volumes. Here's the same material presented as we saw before. Notice I'm emphasizing here that the volume ratio may be used in place of a mole ratio. Does not mean that 1 mole occupies 1 liter of gas. Here's an example which we can come back to afterwards. But what we want to do right now is look at the idea of a molar volume. This is something we'll empirically determine in the class. And here is essentially what a molar volume looks like. It's the volume of 1 mole. It would be 22.4 pot bottles. So in this case, those would be 2-liter bottles. So we'd need about approximately 12 of them, or maybe 11. Okay, so in the molar volume, it's depending on the conditions. 22.4 liters would correspond to. If we come back here to the other handout that you received, we're going to look at the molar volume of a volatile gas in the investigation in the section. So you'll want to go through and read that for sometime in the next couple days, investigation 10.2.1 on 472. But in this investigation, we're going to try to determine the molar volume of a gas under lab conditions. Experimental results have shown that the volume of a gas at a fixed temperature and pressure is constant. And typically this volume we would give at either standard temperature and pressure, which are these conditions here, or standard ambient temperature and pressure, more convenient, would be those conditions here. So a little closer to room temperature and atmospheric pressure. Notice that the change in temperature and the reduction in pressure produces a slightly higher molar volume at standard ambient temperature and pressure, and that's consistent with the gas laws that connect volume and pressure, and volume and temperature. Now, there are slight, what are called deviations from molar volume, and these are described in your textbook on page 469. You'll see some types of gases in the margin there. Real molar volumes can vary from as little as 22.097 for ammonia up to 22.433. So not much change there for hydrogen, carbon dioxide, nitrogen, and oxygen. But for ammonia, because it has polar bonds, ammonia does have intermolecular forces that are fairly significant. The ammonia molecule would have, just to simplify here, delta positive dipoles on the hydrogen atoms and delta negative dipoles on the nitrogen. So as a result, the dipoles are going to interact, and there will be some intermolecular forces acting between these molecules. What that's going to effectively do is to decrease the ability of the gas particles to just act as random particles moving in straight lines. They will be influenced by other particles, and so the ability of the gas to expand is a little bit diminished because of the attraction particle to particle. So where does this number come from, or where do these numbers come from? Let's have a look at just maybe one example. We can use the ideal gas equation. You may have seen this before, already shown to you in a previous question or an example, that if you just use 8.31 as your ideal gas constant, and standard temperature and pressure is 0 degrees Celsius or 273 Kelvin, and then standard pressure is 101.325 kilopascals. And if we assume 1 mole, then the volume that would occupy under those conditions would be called the molar volume. So we're solving for volume here, and it would be the product of mole gas constant and temperature over pressure. So if we put in 1.00 mole 8.31 kilopascal liter per Kelvin mole for a gas constant, 273 Kelvin, and divide that all by the pressure at 101.325. We should get a value really close to 22.4. Let's just compare. Okay, so there's our final answer, 22.3896, around that to 3 significant digits, and would be 22.4. Notice when you put the units in the formula, it's really obvious how we end up with volume units, because liters is everything left over after we've canceled out temperature, mole, and pressure units. So you can also confirm for standard ambient temperature and pressure, which is 20 degrees Celsius and 100 kilopascals, and assuming your 1 mole again there, same gas constant, you can confirm that as well. Okay, so that's in your handout for you to do on your own. Should get a value of pretty close to 24.8. Okay, so we've got molar volume, we have the law of combining volumes, and we have the theory of equal volumes at same temperature and pressure containing the same number of particles or molecules. So now how do we apply this? One interesting application is to look at the decomposition of hydrogen monoxide, dihydrogen monoxide, or water, into hydrogen gas and oxygen gas. And here, in this case, when you take water, slightly acidified so that it has some conductance to it, and I'll try to demonstrate this in class if we have the apparatus set up. Liquid water decomposes to its element gases, and you'll find that when you observe the tubes containing the product gases, the volumes are actually very close to the 2-to-1 ratio. So when we balance this reaction equation, we get 2 moles of water decomposing to 2 moles of hydrogen and 1 mole of oxygen. Now, we cannot apply the molar volume to a liquid, but what we can do is say that anything that is a gas in the reaction will connect to another gas in the reaction by a mole ratio, of course, or also by a volume ratio. So that means that approximately 2 parts, or we could say 2 liters of hydrogen are going to be formed for every 1 liter of oxygen. In this case, you look at the water molecule and you'd say, well, what's it made up of? Well, it's made up of 2 parts hydrogen, 1 part oxygen. So it's not a surprise there that when that decomposes, you're going to get 2 parts to 1 part. And here, if you look at the figure 1, you'll see this hopefully in class, that the amount of gas produced in this part of the apparatus would be approximately double to the other part. Okay. So here's a simple sample problem to apply the law of combining volumes. If we have the combustion of carbon monoxide into carbon dioxide, and we have 125 liters of carbon monoxide that is reacting, we're trying to determine what volume of oxygen would be required. In this case, we don't know the conversion from liters to moles. We would, in that case, need to know the density of carbon monoxide and have to work that out. But in the application for law of combining volumes, we can just simply look at the mole ratio and know that the volume ratio will adhere to that exact same whole number fraction. So because the mole ratio is 2 moles of carbon monoxide for every 1 mole of oxygen, or put a slightly different way, that 1 mole of oxygen for every 2 moles of carbon monoxide, we can determine the moles of oxygen by simply multiplying by 1/2 or dividing by 2. So we'd end up with 62.5 liters. And so that's a really direct application of that law of combining volumes. So stoichiometry with gas phase reactions doesn't necessarily need to involve the familiar formula, moles equals mass over molar mass. We're more likely going to be using the molar volume. Okay, and so the molar volume will be something that will be very useful when we do stoichiometry with gas phase reactions. Okay, I'd like to go through a couple more sample problems here just to reinforce this concept. This one here, what amount of oxygen is available for a combustion reaction in a volume of 5.6 liters? So what amount there in moles? Well, if the 5.6 liters is oxygen, then we know that it's less than 1 mole because the molar volume at standard temperature and pressure is 22.4 liters. So we can just do a simple comparison of the molar volume to the actual volume that we have. And here again, the conversion is just multiplying by an equivalence, that there's 1 mole for every 22.4 liters. And we can directly convert liters into moles that way. Almost the way we would convert say a mass into an amount in moles. We could take 1 mole for so many grams. Let's suppose we were working with cesium and its molar mass is 132.91, and we would know that for cesium that's its molar mass, and if we were to multiply that by let's say 100 grams, then that would convert us into moles, and that would be a little bit like taking mass and dividing by molar mass. When we use a equivalence, we can just multiply, and here you'll see that the molar mass is still in the denominator, so it's going to involve division or the multiplication of the reciprocal. So that would give us a final answer in moles. Okay, and so that would be consistent with the formula that we know there. So here our conversion from liters to moles doesn't need to involve a formula, it just needs to involve a conversion factor, which is simply going to be the molar volume. And of course, it really wouldn't matter whether we're talking about 5.6 liters of oxygen or 5.6 liters of carbon dioxide. We would maybe want to check to see if the molar volume of the gas is deviating from the true value to 22.4, or I call it the true value, but the average value. In the case of carbon dioxide, it's a little bit smaller. Ammonia is significantly smaller, almost down to exactly 22. So if you know the identity of the gas, you can certainly use its known molar volume, and I can just refer you to the margin on page 469 for that. So let's keep going here. Looking at sample problem 4. The propane tank for barbecue contains liquefied propane. Tank mass drops by 9.1 kilograms after a month's use. What volume of propane gas at standard ambient temperature pressure was used for cooking? Now here, we're going to need to know how many moles that was, because it says a liquid in the cylinder, and its tank mass is dropping by a kilogram amount, not a volume amount. So what we can do here is convert the mass into moles, and then we can determine what volume that corresponded to under the conditions of ambient temperature and pressure. So here, propane, if you didn't know, is C3H8. Its molar mass is 44.11 grams per mole. So we'll convert that into moles. What's done here is, at first, it looks like a real mess of calculation, but what's actually being done there is you're taking a mass and you're actually dividing by a molar mass, so you are calculating a mole value right there. You can, at some point, if you trust this, you can use a prefix of a unit as just an additional factor, and you don't have to actually convert into grams. Kilograms divided by a molar mass is going to give kilomoles. And so if that doesn't work for you, well, then convert into grams, but you'll notice how they cancel out grams and they don't cancel out the K, because K represents essentially 10 to the 3 or 1,000 of whatever you want, okay? So your answer there is in kiloliters. Why? Because there we're using, under ambient temperature and pressure, the molar volume, and the molar volume under those conditions is 24.8. So it'd be a lot like the conversion in sample problem 3. I would encourage you maybe to do that in steps. First convert to moles, and then tack on your conversion factor here for the molar volume as an additional step. Final answer, notice again, it's in kiloliters. Well, you've got a significant amount of propane that's been used, so it's going to be 5.2 thousand liters. Whenever possible, I would increase the unit rather than increasing the number. 5.2 times 10 to the 3 would be the answer in liters, and 1,000 liters. Again, if you didn't know that already, 1,000 liters is equivalent to 1 cubic meter. So if you can picture a cube, a meter on each face, then that would be a cubic meter, obviously, of volume inside, and that would occupy 1,000 liters. Okay, so the answer was not required in cubic meters, but that's just another way of representing. So summary of concepts here, we have the law of combining volumes, which is simple whole number ratios for gas phase reactions. Reactants and products are related by simple whole number ratios. We have Avogadro's theory, which is that equal volumes of gases contain equal number of molecules. And then we have the 2 molar volumes which have been looked at. So again, going back, confirm the molar volume under ambient temperature and pressure. Go through the procedure for the molar volume. I think we're going to do this as a class as far as pooling our results all together, but I'll have you work on it in a small group so we can at least get some precision and find out how consistent we are at measuring the molar volume for a volatile liquid. That would be something that would have a significant vapor pressure at room temperature. And I've also included in the package here some extra practice questions, and the solutions are on this page following. And I'll just go back to the slides that you received here. This one summarized the same idea, just with maybe slightly different examples or wording. And you can go through both of those just to compare the information. And at the bottom of the second page, you have the assigned questions which we'll work on in class. So hopefully this is starting to make some connections between some of your gas laws, the ideal gas laws coming in, and also stoichiometry, so that you can see how this ties in with previous content. So we'll see you in class tomorrow, and we'll be working on questions as well as the molar volume activity as a group.